And today's talk is nuclear forensics. Right, what is it? You all heard of CSI. Probably all watched it, right? Has anybody not watched CSI? One man down here, one man over there. So pretty much everybody's watched CSI. So everything you see on CSI, forget it. It's wrong. You can't do it that quickly. Not at all. But some of the methodologies that you see in the program, yes, indeed, they do use some of the methodologies. And some of the leaps of faith they're making when they're making a conclusion from one observation, they always get the right solution, don't they, from that observation, whereas there could be a plethora of solutions to how that observation was made, but they always get it right. We don't always get it right. You'll see in some of the case studies how we didn't always get it right. Anyway, what is nuclear forensics? It's the analysis of nuclear materials that are present at the scene of something. It could be an intentional act, it could be an accidental act, and you need to trace it back. And in one example, it is actually a natural occurrence that took place billions of years ago that forensics were used to figure out what was going on. Although, when I use the term forensics, what it generally means is there's going to be a court case, because forensics is the chain of custody with the analysis of the material to prove something in a court of law. And it is a different process to just making a measurement in a laboratory and coming to a conclusion. There's all kinds of procedural rules that you have to follow to make sure that the evidence is substantiated when you're in court. This is the periodic table of the elements. Everything in blue, there, is mostly stable. Everything not in blue is radioactive, meaning there are no stable isotopes of that particular element. And down on the bottom, there are the well-known ones. There's uranium, neptunium, plutonium, americium, and curium. You've probably heard some of those names. And actually the one before uranium over there is thorium. But that's not the whole story, because the stable elements, don't think that this is just our only problem, the ones that are in blue. The stable elements also have isotopes that are radioactive. And there's one, there's another, and there's a third. I just gave you 3 examples. Cesium, you've probably heard of cesium-137. You've probably heard of strontium-90. Cesium-137 and strontium-90 are fission products. They are left over after nuclear explosions. They are left over in used fuel. And at the top there's cobalt-60. There's another one, cobalt-57, which is radioactive. The cobalt-60 is very common in hospitals. If you've ever had a radiation treatment in a hospital, it's likely to have been a cobalt isotope that delivered the radiation in your treatment. It could have been cesium as well. But there are many others that are used in nuclear medicine. Shown here is an alpha particle and an electron, and the gamma is simply electromagnetic radiation. So, alpha decay. Americium changing to neptunium here, emitting an alpha particle, highly energetic, massive in terms of nuclear particles. It's very heavy relative to an electron, meaning it doesn't travel very far. It doesn't travel very far in air. It travels even less in your tissues if you get it inside you. More about that later. Measuring it, we have this beautiful, tight fingerprinting with alpha radiation. They're monoenergetic. So if you get the source in the right shape and size, put it in the right detector, you'll get a picture like this. Now, beta minus decay, beta plus decay. Something can decay, transmutate, and it will emit either an electron or a positron. And a positron is simply the antiparticle of the electron. On the top, you've got carbon going to nitrogen. It's emitting an antineutrino and an electron. And down below, you've got carbon-10 decaying to boron. It's emitting a neutrino and a positron. That positron is antimatter, it will annihilate straight away, you'll get a 511 gamma line too, and that's another fingerprint. The problem with this decay mechanism, this emission type, unlike the previous one, is if you measure the spectrum, it looks like this. It's smeared out, and that, by the way, is what the alpha particle spectrum will look like if you have the wrong source. It will be smeared out, not exactly like this, it will be a different shape, but it will be smeared. So, how do we measure them? Well, as I said, you can fingerprint these, but the problem now in measuring the gamma rays is what detector do you use, because the detector really influences how you can figure out what is emitting those gamma rays. And this picture shows you 3 detector types. At the bottom, CZT, cadmium zinc telluride. It's able to be used at room temperature. It's an intermediate resolution device. Above it, in red, is the hyperpure germanium detector, which has to be cooled to liquid nitrogen temperatures to operate properly. And you'll see very sharp peaks using the germanium detector. And that, by the way, is pretty much the industry standard now, at least in the Western world, using germanium detectors. And then the top one is sodium iodide. That is a crystalline type of detector. It is a low-resolution device. And so you see things are smeared out. Those 3, the black, the red, and the blue, are measuring the same thing, but you're getting different results depending on the detector. This peak here, the big blue peak, is predominantly iodine from a medical treatment, iodine-131. It so happens that plutonium emits gamma rays in the same region. If you want to conceal weapons-grade plutonium, you add iodine-131 to your container, and the detector will see iodine-131, and you might miss the plutonium if you're using a sodium iodide detector. If you're using germanium, however, you can't get away with it. The resolution is sufficient that you can separate the peaks here. So that one is very much detector dependent. But now we'll go to some examples and some case studies, some of which I was actually involved in. There's radiation everywhere, but I'm digressing. So let's talk about Chernobyl. Where did the fallout go? If you think it just stayed in Russia, you're wrong. It went absolutely everywhere. It went all over the planet. In some places, it fell more than others. We in Canada, I was working at the Radiation Protection Bureau at that time, were concerned with what was going on in the Northwest Territories, because the air models showed it going up in the north more than the south. The source term was many different radioactive isotopes. I've given you the predominant ones here, cesium-137 and cesium-134, and the amounts that were emitted from Chernobyl. It's measured in pettabecquerels. Peta, I know you don't have a clue what that is. We use it so rarely. It is 1 times 10 to the 15. That's a 1 with 15 zeros after it. So it's a big number. There was a lot of it released for both cesium-137 and 134. This is what they look like as they decay. This is almost 3 years. But you'll see the 137 is hanging around longer than the 134 because its half-life is much longer. Well, this is not particularly informative, just looking at this. But if you ratio them, it is more informative. You see that that ratio changes steadily with time. So if you know when the source was emitted, as we do exactly with Chernobyl, you can calculate what this ratio is supposed to be when you measure the cesium isotopes, because it's the same element, so the chemistry is the same, they will follow each other. Well, what was found, surprisingly, that only 25% of the radiocesium that we were measuring up in the Northwest Territories was due to Chernobyl. Surprise, surprise, the rest of it came from the bomb tests in the 60s, and nobody knew that it was still there. That is because of the ecology up there. It's a very strange ecology. Cut to the chase, the highest dose that we figured happened in the Northwest Territories was 0.4 millisieverts per year. We know that unit doesn't mean anything to you. Take in mind that the background dose to all of us is somewhere between 2 and 3 millisieverts per year. So it was a very small fraction of natural background. So it wasn't an issue for the people that lived up north. Here's some pictures from that study. Over on the left, the 2 Quonset huts, that's the Baker Lake Hotel. taken in the winter. Yes, we did this in the winter. Why? Because that's when everybody's there. In the summer, they disappear off into the land and they go hunting. Over on the right, there's a picture from Baker Lake. On the lower left is Baker Lake from the air. On the lower right is Baker Lake from the air again. There's the hotel. There's the medical center. I spent 5 weeks there in the winter. Here's some pictures. We had school children helping us when we were doing these measurements. You see the radiation detectors there. Shamefacedly, I admit, these were low-resolution detectors in those days. We didn't have the money for the fancy stuff when we did this in the 90s. Here's some more pictures of the studies. On the top left, we're flying up to Old Crow over the mountains. There's Old Crow on the right. It's a raven, not a crow. It's so quiet there, as they fly overhead, you can hear the beat of their wings. You'll see a couple of clients on the lower left. And I love the photograph on the lower right, because that's the airport terminal in Old Crow. Number 5. Number 5, I was involved in this myself. Does anybody recognize this individual? No? No, you don't recognize this individual? Alexander Litvinenko. Does that name mean anything to you? He was poisoned, yes, you're very right. And he's dead. He's buried in Highgate Cemetery in London now. This is his grave. And we will go through this. So this is the timeline of what happened to Alexander. Alexander Litvinenko was a dissident, very vocal against Putin, and it turns out was also an employee of MI6. But that wasn't known until much later. So here's the timeline. 1st of November, he meets with some Russians at the Millennium Hotel in London, and he also meets with some others in the Itsu Sushi Bar, Piccadilly. That night, he becomes seriously ill. That night, I want to stress it, it's that quick. He became seriously ill. Vomiting, couldn't sleep, diarrhea, awful. He checks himself into hospital on the 4th of November, having suffered for 3 days. And as you see there on the 11th, he's being described as in very bad shape because it is just getting worse. He is then transferred to another hospital on the 17th of November, and he is placed under police armed guard. The fact that police were involved so early on in this is probably because of the MI6 connection, and the fact he was a dissident. Here's the pictures. So there's Alexander before and after. And one of the things is hair loss. You see all his hair has gone through the radiation damage. There's some pictures of the police, one standing outside the Millennium Hotel. The Itsu Sushi Bar was closed while they did their investigations. It's reopened now. There's the Millennium Hotel. The teapot on the lower right is believed to have been the delivery vehicle of the poison. The poison was added to tea, which Litvinenko ingested at some point during that day, and then later that night started to get sick. The little map there shows you some locations in London that were identified as being radioactive. Here's some more. Where was plutonium found? Well, there's London. It was found in Hamburg. It was found in Moscow. It was found around London. It was actually found in a football stadium. It was found on aeroplanes. That was one of the things we had to deal with. People were concerned. They had flown to London. Were they in danger of picking up polonium-210? We find out that they weren't even on the plane that was contaminated. We find that they hadn't even flown to London until after the incident had happened. So a lot of fear. But nonetheless, one of the things that was found out during this investigation on planes is the airlines move seats. And some of the radioactivity was found on seats in storage. His blood, God knows what was going on in his blood, some very strange chemistry at these high radiation levels, because about 200 times the lethal dose was in his body. How was it discovered? This is a gamma ray spectrum. An enterprising scientist at the Atomic Energy Weapons Establishment in England did a long count on some biological material from him, and it is this little peak here that identified the polonium-210. It's very weak in intensity, as shown on this diagram. So there's the polonium-210, 138-day half-life, predominantly decays by alpha decay right to the ground state, but 1,000th of it, of those decays, 1,000th of those go to an excited state which emits a gamma ray. It's very weak in intensity, so it's easy to miss. That's how it was discovered. How much in terms of mass? Hard to say really. About 10 micrograms perhaps. That is equivalent to 200 times the lethal dose. To give you an idea of how dangerous this material is, if you do the calculations with a gram of polonium-210, you could poison 100 million people. And of those, 50 million would die, because that's the LD50, the point at which half of the people will die for a given dose. So it's lethal. Incidentally, don't think that's the only time you can be exposed to it. If you eat shellfish, it's there, and the amount varies by a factor of 90 depending on the fish you eat. You could get up to 0.5 millisievert per year, which is about a fourth of background. And if you smoke, you'll have a little bit of exposure for polonium-210 in the tobacco, up to 1/10 of the natural background dose. So, conclusions. If you want to do nuclear forensics, you've got to know a lot of supporting sciences, because it's multidisciplinary. You've got to have an understanding of the radioactive processes, the types of radiations that are emitted, and how to detect them. And you've also got to be able to understand all the electronics necessary to optimize those measurements that you make. And I showed you one example when we were looking at the gamma emissions. You've got to choose the right detector for the right job. If you use a low resolution device, you could miss something very important. And that brings me to a very brief tour of nuclear forensics. And I think we